solutions from exercise 1.2 from the first chapter, Real Numbers. So the first question, they've asked us to prove that root 5 is irrational. So in order to give the proof, we're first going to assume that root 5 is rational to the contrary. So if a number is rational, then we know that it can be expressed as a by b, where b is not equal to 0. So thus we can say that root 5 can be expressed as a by b, where b is not equal to 0. We're also going to assume that the numbers a and b are co-prime integers, which means that it only has 1 as its common factor. So now that we've said that number root 5 can be expressed as a comma b, we can write it down as root 5 is equal to a by b. Now this is going to be the first step. So in the second step, we're going to square both sides of the equation. So when we square both sides of the equation, we'll get root 5 squared is equal to a by b whole squared. We know that when root 5 squared is equal to 5, because this and this will get cancelled. So we can say that 5 is equal to a squared by b squared. Now, in the next step, we're going to bring 5b squared to over here and 5 to the bottom by cross multiplication. So we'll get, when we cross multiply this, we'll get 5b squared is equal to a squared. And now we're going to bring 5 to the bottom, to the other side, to the right hand side. So we can say that b squared is equal to a squared over 5. So now we can see that a squared is divisible by 5. We know that from theorem 1.2, if a squared is divisible by an integer, in this case 5, we can also say that the number a is also divisible by 5. This suggests that the number a has 5 as its factor. So now we're going to assume that a is equal to 5m. Now we're going to substitute this with this equation. So when we substitute the value of a in a squared by 5, we'll get b squared is equal, since we know that a is equal to 5m, we're going to substitute that value over here. So 5m, since there's a square on top of a, we're going to square this as well, divided by 5. So since this square is common to both of these terms, we can write this as b squared is equal to 5 squared times m squared by 5. Now we can cancel this and this, because 5 squared is essentially 5 times 5. So we can cancel 5 and the other 5. So this will give us b squared is equal to 5m squared. Now we can bring this 5 over to the left hand side, which will give us m squared is equal to b squared divided by 5. Similarly from this equation where we said that if a squared is divisible by 5, we can also say that a is also divisible by 5. We can use the same theorem from theorem 1.2. We can say that b is also divisible by 5. Since we have proved that both a and b is divisible by 5, we can say that both the numbers a and b have at least 5 as its common factor. Since we have proved that both a and b have at least 5 as its common factor, this contradicts our assumption where we assumed that both a and b are co-prime integers, suggesting that the only common factors it has is 1. But we have now proved that it also has 5 as its common factor. This contradicts our assumption, suggesting that our assumption is wrong. Since we have proved that our assumption is wrong, then automatically we can suggest that root 5 is an irrational number. Hence proved. In the second question, they've asked us to prove that 3 plus 2 root 5 is irrational. So in order to prove that it is irrational, we are going to assume to the contrary that 3 plus 2 root 5 is rational. If a number is rational, then it can be expressed in the form a by b, where a comma b are co-prime integers and b is not equal to 0. So we can express this as 3 plus 2 root 5 is equal to a by b. We need to isolate the irrational number root 5. So we're going to bring 3 and 2 over to this side. Since 3 is an addition, when we bring 3 over to this side, over to the right-hand side, it becomes negative, so it becomes subtraction. So we'll get 2 root 5 is equal to a by b subtracted by 3. Now we need to make sure that 3 by 1 has common denominator b. So we're going to multiply both the numerator and the denominator by b. So we're going to arrive at the equation a minus 3b by b. which is equal to 2 root 5. So 2 and root 5 are in multiplication. So when we bring 2 over to the right-hand side, it becomes division. So root 5 is equal to a minus 3b by 2b. Since we have first assumed that a and b are coprime integers, we can say that a minus 3b by 2b is rational. And in this equation, we've said that root 5 is equal to a minus 3b by 2b. That means that root 5 is also rational. However, in the beginning, we have taken that 3 plus 2 root 5 is irrational to the contrary. And we know that root 5 is irrational. That means our assumption is wrong. Since our assumption is wrong, we can say that root 5 is irrational, then 3 plus 2 root 5 is also irrational. Hence proved. Moving on to the third question, they've asked us to prove that 1 by root 2 is irrational. So similarly to the first two questions, we are going to assume that 1 by root 2 is rational to the contrary. Then it can be expressed as a by b, where a comma b are coprime integers and b is not equal to 0. So this can be written as 1 by root 2 is equal to a by b. So unlike in the previous questions, the irrational number is on the denominator and we need it to be on the numerator. So we can achieve that by cross multiplying. So when we cross multiply, we'll get b is equal to root a root 2. Now we're going to bring a to the left hand side, which will give us b by a is equal to root 2. So similarly in the first two questions, we're going to square both sides. So when we square both sides, we'll get b by a whole squared is equal to root 2 squared. When we further simplify this, we'll get b squared by a squared is equal to 2. Now we're going to bring a over to the right-hand side and 2 to the denominator on the left-hand side. By cross multiplication, we'll get b squared by 2 is equal to a squared. From theorem 1.1, 1.2, we can say that if b squared is divisible by 2, then b is also divisible by 2. Now we're going to assume that b is equal to 2m. We're going to substitute this in this equation we're going to get 2m whole squared by 2 is equal to a squared. Since this square is common to both the terms inside the bracket, we'll get 2 squared m squared by 2 is equal to a squared. So this and this will get cancelled. You'll be left with 2m squared is equal to a squared. Now we're going to bring 2 over to the right hand side, so we'll get m squared is equal to a squared divided by 2. From theorem 1.1, from theorem 1.2, we can say that a is also divisible by 2. We have now proved that both the terms a and b are divisible by 2. But in the beginning, we have assumed that both a and b are coprime integers which do not have any other common factor other than 1. However, we have disproved that by proving that both a and b have at least 2 as its common factor. So we can say both a and b have at least 2 as its common factor. This contradicts our assumption that a, b are coprime. Hence, our assumption is wrong. And 1 by root 2 is irrational. In the second question, they've asked us to prove that the number 7 root 5 is irrational. So, we're going to assume that 7 root 5 is rational to the contrary. Thus, it can be expressed in the terms of a, b, a by b, where a, b are coprime integers, and b is not equal to 0. So we can write this as 7 root 5 is equal to a by b. We need to isolate root 5 because it's irrational. So we're going to bring 7 to the other side. Since this is in multiplication, when you bring it over to the right hand side, it becomes division. So root 5 is equal to a by 7b. We know that a and b are integers, so that means that a by 7b is rational. Since we have written that root 5 is equal to a by 7b, then root 5 is also rational. However, we know that root 5 is irrational. Thus, we can say that it contradicts our assumption. It contradicts our assumption that 7 root 5 is rational. Hence, 7 root 5 is irrational, hence proved. In the third question, they've asked us to prove that 6 plus root 2 is irrational. So we're going to assume that 6 plus root 2 is rational to the contrary. Then it can be expressed as a by b, where a and b are co-prime integers and b is not equal to 0. So we can write it as 6 plus root 2 is equal to a by b. In order to isolate root 2, we're going to bring 6 over to the right-hand side. Since it's addition, it becomes subtraction. So we can say that root 2 is equal to a by b subtracted by 6. Since this is a fraction and this is an integer, we're going to make sure that the denominators are same. So you're going to multiply by b in both the denominator and the numerator. So you'll get root 2 is equal to a minus 6b by b. We know that a minus 6b by b is rational because we have in the beginning taken that a comma b are integers. So that means root 2 is also rational. However, we know that root 2 is irrational. This contradicts our assumption. This contradicts our assumption that 6 plus root 2 is rational. So that means 6 plus root 2 is irrational. Hence proved.